My background is, oh, hello. Okay. Um, yeah, my background is in statistics, but this is not going to be a very statsy talk at all. So those of you that are visiting the department, don't worry. There are no equations. There's a few Greek letters, but that was really just for form as much as anything. And so what I'm going to talk about is what we do at World Weather Attribution, which is extreme event attribution. And hopefully to convince you why this matters as well, because it's a tough time to be a climate scientist in many ways. The field is kind of under attack at the moment, so this feels like a very good time to be spreading the word about attribution science and why we need to understand these kind of phenomena. Oh. So you may or may not know what attribution science is. If you don't know what I'm talking about, you've probably seen headlines, especially if you're a reader of The Guardian or similar. The kind of headlines that say things like climate change made this heat wave more likely, climate change made this heat wave more intense. These are attribution headlines. So taking a step back, it's not a proper stats talk if it doesn't have an SKCD in it. We've known for a very, very long time the effect that putting more CO2 and other greenhouse gases into the atmosphere is going to have. Predictions from even 100 years ago of the response of atmospheric temperatures to greenhouse gas concentrations, they are surprisingly accurate. So this is not new science. Understanding that global warming is going to happen in response to CO2 concentrations, hopefully, no one is surprised to hear that. No one thinks that's contentious in this room. And what attribution science is about is trying to understand how we move from those global changes to what's happening in the local weather. So this is a really nice graphic that I've pilfered from Ed Hawkins, who is very good at visualizing this kind of thing. If you don't already follow him on Blue Sky, I recommend you do if you're interested in this kind of thing. Just showing the kind of steps of the causal chain that we're trying to understand when we do attribution science. So we've got a good handle on what our global cumulative CO2 emissions are. That's the line at the top here. And we actually know that more than 100% of the forced change in global mean surface temperatures, which I will almost certainly say GMST without thinking about it, so that's what I mean when I say GMST later, almost more than 100% of that change is driven by anthropogenic CO2 emissions. I say more than 100% because some human activity actually causes a cooling effect that counterbalances that. So we have a very strong attribution from CO2 emissions to global temperature changes. And that means that when we're attributing changes and saying that they are caused by global mean temperature changes, we're using that as a proxy for the CO2 emissions that we put in the atmosphere. We know that's us, that's our fault. So what we really want to understand in attribution science is how we get from this orange line of global temperature change to what's happening in the local weather. So in this case, this is UK rainfall intensity. And it's quite a nice example because you can see visually right away that rainfall change tracks against the GMST change. And what we want to understand in attribution is how much of those changes in rainfall are due to those changes in GMST and thus to human activity and emissions. So there are kind of two parts to the question that we're trying to answer. When we want to understand how was a particular extreme weather event influenced by climate change, we want to understand, are events of a similar magnitude now more likely, and how much more likely or less likely? And are events that occur with similar rarity now more or less intense? So they're the kind of two key questions that we want to keep in mind. There we go. I will talk more about the kind of science that we do in a minute, but I want to just pause and look at why this matters. So 20 years ago, this is what the BBC officially said to their journalists. No single weather event can be linked to climate change. You cannot say that climate change made this event worse. You cannot say it made it more likely. 20 years ago. And this was only removed in 2018, which really surprised me. I would have thought that for a longer period than that, we would have been able to talk about climate change and what it's doing to our local weather, but no. And yesterday, as Richard said, this was a BBC headline based on a study that we just published about the effect of climate change on the Los Angeles fires. I don't like this example because that's kind of mischaracterizing what we said. So I'm also going to show what The Guardian said, which is much more nuanced. We did not say that it made the fires themselves more extreme. We were very careful not to say that. This laptop is very slow. There we go. What we did was we looked at different strands of evidence, all of which are showing that fire conducive conditions are getting a little bit more likely, and that meant that those fires were more likely to happen. It's a subtle difference, but it's quite an important one when you're talking about those two different attribution questions that I showed you earlier. So that's in 20 years. We've really shifted the conversation using attribution science on what we can say about climate change. And this is actually just summarizing a few of the results that come out of the IPCC's last assessment report. This is Working Group 1, Figure 3. And this is just talking about what we can say about the effect of climate change on extreme hot temperatures across the world. So each of these hexagons represents a region. And as you can see, almost everywhere in the world, we've got strong confidence that hot extremes are increasing, which is not very surprising when you think about the physics. And there are a couple of regions in here where these grey hexagons indicate we just don't have enough studies to be able to do that analysis. There are also a couple of areas in North America where there's what's known as a warming hole, where it's actually getting cooler, but there are some circulatory reasons behind that, which I will not go into. So temperatures, it's quite a clear pattern. This is the equivalent for heavy precipitation. Climate science students know probably about the Clausius-Clapeyron relation that suggests that for every degree of warming in the air temperature, you would expect it to hold another 7% of moisture, so you expect heavier precipitation. Stats people, you learned a thing. So we would often expect more heavy precipitation, but actually we only have an attributable signal in mostly the northern hemisphere in some regions. And this just shows why it's really important that we keep doing these attribution studies, because there are large parts of the world, especially in the global south, where we know there are huge impacts from these kind of events, but there just isn't enough data, we don't have enough studies, we don't have enough information to be able to assess the overall impact. So what I'm going to talk about now is how at World Weather Attribution we carry out our attribution, and we produce reports like those two headlines that I showed you earlier. There are other ways of doing attribution. It's quite a wide field. There are model-based approaches. This is what we do. We produce rapid studies. Our aim is to get our studies out while people are still talking about the event. So while people are still talking about the wildfires in the US, for example, there's always a lot of discussion in the media. There's always a lot of people throwing opinions around saying, oh, this was definitely all climate change. This was not climate change, this was mismanagement. And it's really useful to be able to have a rigorous assessment of what the evidence actually says while that discussion is still going on. And that's what we aim to kind of contribute to. So because we do rapid attribution, our results are not peer-reviewed before we publish them, before we put them to the press. I was expecting more gasps of horror at that. But in order to ensure that our results are as robust and that we can have as much confidence as possible in them, we always follow a fixed protocol, and we use a set number of methods that we don't really deviate from, so that we know that those methods are peer-reviewed and we can have more confidence in the results that they're producing. And as you'll see, they're quite simple statistical methods, but it means you get a nice clear story at the end of it to be able to give the kind of the big picture to the press, which is generally more useful than coming out with maybe a more sophisticated statistical model that then is very difficult to explain what's actually going on. So we have this 8-step protocol that we always follow. Most of this talk will focus on points 2 to 6, which is the kind of modeling bit that we do. But the other 3 points are actually really important as well. So the way World Weather Attribution works, we will only study events that have had big humanitarian impact. So we work with the Red Cross Red Crescent Climate Centre, and they will produce a weekly report of events that have reached a certain threshold in terms of their impact. So people that have died, people that have been displaced, people that have been affected by a particular weather event. And that's the basis that we choose to study them on, not, oh, it was a big, interesting dynamical storm, let's understand more about the kind of dynamics behind it. Once we've done that, we come up with an event definition. So we will work out what actually is the kind of weather event that we want to look at. I'll talk a little bit more about that in a minute. We look at trends in the observations, we combine those with climate models, and then we produce an overall result. And that's what I'll go into in a little bit more detail. But the last two steps are also really important because it's not always climate change. It's not just climate change. With a lot of these events, especially in the global south, the reason that these events have such terrible impacts is because people are exposed to them, people are vulnerable to them. So we always say there's no such thing as a natural disaster. What turns your weather hazard into a disaster is people being exposed and people being vulnerable. So being in the path of it and not being able to get out of the way, not being able to protect themselves. So again, we work with the Red Cross Red Crescent Climate Centre, and they will do a very detailed qualitative assessment of what we know about who was exposed, why they were vulnerable, and that goes out alongside all the scientific assessment. And finally, we have a great comms team who work with the Global Strategic Communications Council to put together a press release. We'll write a scientific report that has all the details. We'll do like a human readable version that goes as a web summary, and then we'll have a press release as well. And we'll have a press briefing so that we can answer questions from the press. And that is how we get those headlines, essentially, because we have really good relationships with the press, which have developed over years. So the whole process is kind of key to what World Weather Attribution does. So in terms of actually doing the attribution, the first thing we have to do is identify what is the actual weather event that we want to attribute. So as I say, the event definition is always based on the impacts. We are not trying to find a weather event that is the most extreme or that has the strongest climate change signal. What we want to understand is what led to those impacts. So first of all, decide what your most important kind of weather index is, your weather quantity. Do you want to look at rainfall? Do you need to look at temperature? Do you need to look at humid heat? Do you look at a fire index? And then you have to identify the spatial extent, which can often be very difficult understanding in terms of the geography, the topography, what was the actual area over which this event happened, because you might need to look at a river catchment if you're looking at flooding. If you're looking at a heat wave, they can happen over very large areas. You need to work out, do you have mountains in there that you're going to have different processes going on that you might need to exclude from the area? So there's a lot of expert judgment that goes into this process. And we would always work with local experts, preferably with meteorologists, but also with local Red Cross, Red Crescent experts, to try to work out what is the most appropriate area to look at that led to those impacts. And of course, we also need to consider the duration of the event. Was it one day of rainfall that caused flooding? Was it 3 days of high temperatures that caused heat mortality? And the timing and the seasonality can be really important as well. So temperatures that might, if they happen in the peak of summer, not be that dangerous, if they happen early in the season before people have acclimatized, can have huge health impacts. So they can be really dangerous. So actually looking at the right time of year and understanding how unusual an event is for that time of year can be very important. Likewise, if you have heavy rainfall after the monsoon season's normally ended, it's coming on already saturated ground, and that can be what causes the flooding. So a lot of elements to consider. And the way we do this is we collapse all of that information down to a univariate time series, normally an annual time series, in which we have an observation that captures that weather event, and that's what we're going to analyze. And I will talk a bit about other approaches that we might want to take later on. So this is just an example of the kind of statistical analysis that we do. Stats people, I'm sorry, this is going to be super basic, but this is the slide deck that I normally use when I'm explaining attribution, so this is what you're getting. So this is the Central England temperature series. This is just annual maximum temperatures. I think it goes back to 1884 or thereabouts, so it's a nice example because it's very long. Central England temperature series is the average of temperatures in a triangle from Bristol, London and Liverpool, I think. I don't know why I'm looking at you to nod and confirm that. I think it's that area. So it's not necessarily it's not a temperature that's happened anywhere, but it's a nice long time series, and it's good for as a working example. So this is the kind of data that the kind of time series we'll be looking at. We're not really interested in the trends over time. We're interested in the trends as a function of global mean surface temperature. So this is how I've plotted it here. And all we will do, oh, we're frozen again. Hey, there we go. We use a really simple statistical model. This is the simplest form. We will just fit a linear trend that depends on GMST. And this actually is a non-stationary generalized extreme value distribution because we're looking at annual maxima. And if we put a non-parametric smoother through there, we can see, I mean, there's a bit of an upkick at the end, but generally that linear trend actually does capture most of what's going on in that trend, in that data. In many studies, we will also add other covariates, but for the sake of explaining it, this is the kind of simplest way. Other factors you might want to include would be things like atmospheric circulation patterns, like blocking events. So a blocking event is basically when you get a very large area of sort of static air mass that sits in one place, gets very warm, and you get very warm, dry air underneath. So you get very persistent heat waves, and you also get a lot more fire weather, more extreme fire weather in those conditions. So you might want to take that into account to understand the variability. You might want to take ENSO into account. We very often find in rainfall studies in many parts of the world, people will say, oh, this was an ENSO-driven event and not a climate change-driven event. And actually, when you look at the data, you find that, yes, ENSO has made this one year more extreme, but actually the rainfall as a whole is getting worse as a result of climate change. So it's really important to disentangle all the relevant factors. But for the sake of a figure on a graph, we'll just stick with GMST. So in order to answer one of those two questions that I flagged up earlier, what we're interested in is how much more intense these kind of events have become on average. So the expected change, there we go, in annual temperature in response to a 1.2 degree increase in GMST, which is 2 years ago when I made these slides, was how much warmer we were than pre-industrial. We're now at 1.3 and negotiating. So you see here that in response to a 1.2 degree increase in warming since pre-industrial times, the expected annual temperature has increased by 3 degrees. And this is not at all unusual. Yes, stats people, you might be quite surprised to hear this, but we often find, especially in Northwest Europe, that land temperatures have increased a lot more than the global temperatures. Global temperatures include a lot of sea surface, which doesn't change as quickly, but also turns out we are one of the areas that is warming fastest in the world, apart from the Arctic. So yay. So there will be a lot of high numbers if you look at heatwave trends. And this is not at all surprising. So the other thing we can do with this model, we wanted to look at changes in intensity of events, and we also want to look at the changes in how likely they are. So we can use this non-stationary GEV to estimate the effective return level of an event of any particular, with any particular exceedance probability or return period for any value of these covariates that we put in. So this is just showing how extreme we would expect a 1 in 10 year annual maximum temperature to be over that region. And of course, we can also use that to estimate the return probability or the exceedance probability in the return period of the observed event, which is the 2022 heat wave, which according to this model is a 1 in 800 year event. Obviously, we only have 100 odd years of data. And so that 800 years is going to have huge uncertainties on it and should not be relied on as gospel. One of the difficulties with communicating these studies is that journalists love a number. So you have to be quite careful not to accidentally say, yes, this will happen once every 800 years, because it's very easy for these results to be misinterpreted like that. But what that does tell us is that it's a very rare event. That's how we would characterize that. We wouldn't say it's a 1 in 800 year event necessarily. So the final thing we want to do with this, we've estimated the likelihood of this event in the current climate. We can use essentially a probability integral transform to map all of those points into what their equivalent temperatures would have been in a warmer climate at those values of the covariate, and the same thing in a 1.2 degrees cooler climate, which is what we call the counterfactual climate. Anyone that's worked in kind of causal inference, I guess, is going to be familiar with factual and counterfactual worlds, but it's not always a concept that people are so familiar with. So essentially our current climate is our factual climate, and the counterfactual is we want to understand what the changes are between those two climates. So in this case, the counterfactual climate is just defined as 1.2 degrees cooler. You might say in a neutral ENSO phase, if that's in your model, or in a year with high blocking activity, if that's in your model. So you're essentially picking values of your covariates and saying this is the kind of climate that I want to understand changes with respect to. And so we have those two densities. This is just a schematic, because if you look at these actual PDFs for real temperature data, then for that value, your P1 would be, your observed would be over here, and your P1 would be tiny, and your P0 would be 0, and you get infinite probability ratios. So often for temperature changes, the intervals, the changes are so big that get infinite probability ratios, and find that the temperatures that we're seeing now would have been impossible in a cooler climate without anthropogenic warming. But we take the ratios of those two probabilities, assuming they're finite, and that gives us that probability ratio, which is the change in likelihood, which is the other one of those two questions that I asked at the beginning. So thus far, we have detected a change in extremes, but we haven't done any actual attribution. So we want to show that it is actually caused by, that there is evidence that it is caused by climate change. And there are different strengths of causal evidence that people have put forward for claiming attribution or claiming attributable signals. I tend to think of them in these kind of three categories, according to who is most well known for advocating for them, I guess. We have the strongest form of kind of causal evidence would be what you would call, if I can say it, Pearl causal inference, which is the kind of inference where you would make an intervention, and in your system you would run experiments, and you would understand, you would look at changes once you've run that made that intervention, and without making that intervention, then that gives you your factual and counterfactual. There's also what I would term Bradford Hill causal evidence. Austin Bradford Hill was a scientist who I think in the 60s went up against tobacco companies. So before Pearl came up with causal inference, Bradford Hill was using, I think, 6 strands of evidence that he would use if you had these kind of 6 lines of evidence associated with your model. Then he would say, yes, it's very likely that there's a causal relationship. If anyone was at the Royal Statistical Society, there was a paper on estimating dose response curves, I think in December, and one of the discussants raised this and said, you're claiming that we can only do causal inference when we have Pearl causal inference, but we've been doing this since the 80s, since before anyone knew about Pearl, by basically just bringing together strands of evidence. So this is what that kind of Bradford Hill causality would be. And finally, the weakest form that people sometimes refer to, which I would not want to depend on solely, is known as Granger inference, Granger causality. And that essentially just says if you have a statistical model and there is a lagged effect, then it's probably causal, which I would argue that you need more evidence to say that that's true. And that kind of feeds into the Bradford Hill kind of causality. So what we would say at World Weather Attribution is that you can't say that you've got an attributable signal unless you've done causal inference with some kind of intervention. But of course, we can't make interventions and run experiments on the real world, so we have to use climate models instead. Actually, no, I'll pause on that. So some of the other strands of attribution science that are out there are purely based on interventions in climate models. We use this statistical modeling approach because it's much easier to do quickly, but there are groups, Ted Eppard down in Reading, and there's a group in Oxford who will take climate models that simulate specific extreme weather events, will change the initial conditions to remove the climate change signal and run that model again. So you can do that either with climate models, or the Oxford group is actually doing it with forecast data, with the ECMWF forecast model. So you're basically removing the climate change signal, running your model again, and then you get how intense the event was in your factual worlds, your real model simulations, and then with that climate change signal removed, which is your counterfactual. So in that case, you're conditioning so strongly on the event happening that you can't look at a change in the likelihood of the event happening, because it's always in your simulations, but you get a very good estimate of a multivariate estimate of which aspects have changed intensity in which ways. So again, lots of ways of doing attribution. You couldn't do a whole report in 3 weeks if you were going to do that. It takes too long. So we leave that to them, and we're happy when their results align with our results, which they often do. Well, often do. I don't think I've ever seen them not align. But the approach that we would use is slightly different. So we have to use essentially an ensemble of opportunities, so pre-existing climate models, which have been run with specific forcings, where we know that what's changing in those climate models is the greenhouse gas emissions and the atmospheric composition. So the first step, we will identify climate models that we think are going to do quite well in this region. We need to make sure they've got the seasonal cycle right. If we're interested in an event that happens at a particular time of year, they need to get the seasonal cycle right. They need to get the spatial pattern right, so that we know it's raining in the right places if we're looking at a finite area. And we also check that the index has approximately the right distribution by looking at whether the bootstrap confidence intervals of the parameters overlap, just to make sure there's not something very, very different in the processes in the climate models. And there are two ways that we can use those climate models. We can either use exactly the same approach that we use for the observations, which we would call a transient approach. We fit the same statistical distribution, we get the parameters out, we get the change in intensity, we get the probability ratio. Or some climate models don't actually have a continuous run with increasing forcings. Some are only run for a past period, fixed time slice, maybe 30 years, 50 years, and a present climate period. So for those models, we can't use a transient approach. We would have to just look at how likely are events of a certain magnitude in the past and in the present, and then we can get those differences from there. And these are the kind of results that we get. This is actually an example from the fire study that we published yesterday. So FWI1X is the index that we were looking at. That is the fire weather index, the maximum one-day value of the fire weather index in January in the coastal Southern California region. And the fire weather index is a composite index that takes into account temperature, precipitation, humidity, and wind speeds over the preceding days and months to get an estimate of the fire risk on any given day. So this was kind of correlated, but this was the event that peaked, the index that peaked when the fires started on the 7th and 8th of January. So the top blue bar is our observational data. We only have one observational data set at the moment. Well, in this study, I don't think we'll get more actually, because the fire weather index requires a lot of variables that are not widely available. So we have to use ERA5 reanalysis. The light red bars, which are not particularly red on that screen and are very orange on this screen, they represent results from individual models. Usually we would try to get more models than this, but again, we're very limited in terms of models that have the right resolution for this small area and the right number of variables available. And we're always limited by the amount of models that we can get hold of in the time we have available. The bright red bar with no box around it is the kind of what we would call the synthesized result from the models. There is an algorithm at work, to pick my words carefully here, there is an algorithm that does this synthesis. It's essentially a precision weighting. Sometimes there is an additional term to account for spread in the model means. In this case, the individual model uncertainties are wide enough that the algorithm hasn't added that term. I don't want to get into how the synthesis weighting works in detail, because although in one way it's one of the most interesting bits of the stats, it's something that we're actually still working on and developing. It was actually originally devised by one of the founders of World Weather Attribution, Gert-Jan van Oldenburg, who is very sadly no longer with us. And it's running in Fortran that none of the current team, stop laughing, none of the current team are 100% sure why it's doing what it's doing. So we're trying to understand that, we're trying to disentangle it, but at the same time, we are working on a new way of doing this. So I'm not going to get into details of why this is done as it is, because I know some people in this room have queried that before. But ultimately, what the red bar is showing is a weighted average of what the individual models are saying, a kind of overall synthesized result. And then the purple bar at the bottom is the synthesis of the models and the observations together. And that's the overall result that we would usually work with. So I mentioned before these Bradford Hill criteria. So the interpretation of this figure requires a lot of expert judgment. as a statistician, or often as a climate scientist that has had a stats course, it's very tempting to say that's not statistically significant, therefore it's not a real result. And that's where these Bradford Hill criteria come in. So the 6 criteria that he reported, I had to make a list because there was no way I was going to remember them. If your effect size is so large that you essentially there can't be any confounders that could be causing that large an effect, then that is evidence in favor of causality. Well, we don't have that in this case. One of the criteria is a temporal or spatial relationship with the covariate. Well, we always have that because it's an accumulation of CO2 that's causing those GMST changes. Dose responsiveness. So as your GMST increases, your local extreme increases. Well, we have that in this case. Plausible physical mechanism. This is the one that we usually rely on the most at World Weather Attribution, is talking to the local experts and saying, do we think this is likely to be climate change? Or is this just noise? And we also have questions of, is this coherent with what's already known? So an element of plausible physical mechanism. Have there been similar studies? Are there other related indices that are showing similar trends? And the final criteria is it replicatable? Is it found in similar studies? So those are the kind of criteria that we would be looking at. So going back to this, the way we interpreted this with our local fire weather experts who know far more about what we're expecting to happen with fire weather in California than I do. The observations are showing a slight increase in the index, but it's got very high uncertainty. Well, that's not surprising in this area because it's a really small study area. As I said, it's got really complex topography. It's got mountains on one side, it's got desert on another, it's got coast on the other. And we know that it's also got very high climatic variability, which I can't spell apparently. It's got very variable rains. It's got an ENSO effect. This model did have an ENSO effect in here, but this is only the GMST change. And we're also looking at the peak value each month of that index. So that's also going to increase the variability. But what we also see is that of the 6 models that made it through that validation step, that evaluation step, 4 of them show a trend not only in the same direction, but of a similar magnitude. And none of the models actively show an opposite trend. And actually, this was only one of 5 lines of evidence that we looked at in that fire study. We also looked at changes in the timing of the end of the dry season, changes in October to December precipitation that feeds into this index. There was a separate study that looked at modeled burn area, not in this attribution framework, but in a different modeled framework. And there was a 5th line of evidence looking at changes in circulation patterns. So even though all of these changes individually were very small, they are all leaning in the same direction to suggest that there is an influence from climate change increasing the fire risk in this region. So even though these numbers alone may not give us great confidence in that, when we combine them with those other lines of evidence and with our physical understanding, we can actually make a reasonably strong statement. But there are definitely some limits to this method and what it can do. In terms of the way we combine results, it's only applicable for a single univariate index. So the numbers on the left and the numbers on the right are synthesized independently. That's definitely something I'm working on adjusting. Actually, in this algorithm, models and observations are treated slightly differently, which is something that we need to work on. And there's no link between observed past and future trends when we do this synthesis. They're all done independently. So when we look at climate models and what they project under further warming, we'll only have the model data. We don't have the observations, which in this case, you would get the same result. In fact, we did get the same result. It's a 35% increase in the likelihood of similar fire weather index values. But when you're looking at things like temperatures, where there are processes missing in the climate models, and your observations may show a much stronger signal, you can get very different results for the attributable trend so far and the future trend, which makes it very confusing to communicate, I think. I very much won't go into this in detail, but there is future work planned. This is what I wanted to present, but haven't had any time this month to work on. Future work is planned to develop a more flexible framework for combining models and observations. So this is just showing the kind of the structure of the problem that we want to solve. So what we want to learn about is the anthropogenic warming effect. On the one side, with observed changes, there may be other factors promoting that change. There might be ENSO, there might be deforestation, there might be feedbacks that are not directly anthropogenic warming related, but that are producing a similar signal. Those factors we don't expect to appear in the models, but the models may have other model biases due to missing processes. And we know this is the case. And so the difficulty here, and this I would love to hear if anyone has any ideas on, is how we disentangle where that anthropogenic warming effect sits between the model results that we're getting and the observational results that we're getting, how we narrow down which side is other factors and which side is model biases, and how we can kind of split those two out. And there are some hazards and some regions where we have really good evidence. So as I mentioned, we know that temperatures in this part of the world are warming much faster than climate models would say they are. And there's actually been a couple of recent papers showing that there are missing changes in circulation patterns that are bringing much more hot air up from Africa. And that doesn't happen in the models. And that's why temperatures in like annual maximum temperatures in Northwest Europe have increased by maybe 4 degrees, and the climate models would say 2 degrees. So in this case, we're pretty sure that's a model biases error, because people have done simulations to test that, and they've found that that increase, at least 1 degree of it, I can't remember the exact number, but a sizable portion of it is due to model biases. So that would allow us to narrow it down. But any further thoughts on how we can narrow that further would be great. And this is how I plan on developing that framework, which is pretty much already exists. It just needs some minor tweaks based on some work that Richard did and that I used in my PhD, which I was possibly going to talk about more, but given the time, I will not. And there are lots of other interesting modelling questions that I would really like to get people's interest on, people's views on. How can we accommodate record-breaking events in these models that suddenly spike like that 2022 value did, way above what we have ever seen before? Better constrained GUV and return period estimation. I've already been talking about this at lunch, but also things like better spatial modeling. So as I say, this is very much a univariate approach, and partly that is because, well, mainly it's for practical reasons. We've now reached a point where we can't do a multivariate attribution because the synthesis is univariate, so we need that flexible framework to allow more flexible attribution models. But questions like, how would we look at changing likelihood of a storm anywhere within a region rather than averaging the rainfall over that region when events might move around? That's quite an interesting, tricky one to deal with. And a very big subject at the moment in attribution is compounding or cascading events. So events that happen in quick succession. If you've been following the wildfires, the coverage, you may have heard the term climate whiplash, which feels like it's everywhere at the moment. Has anyone heard that? Or is that just, I'm very exposed to this, so no, I'm seeing confused faces. So climate whiplash is when you go from extreme drought to extreme rain and back again very quickly. So your climate is getting more variable. There may not be a mean trend, but the variability is going up. And that's partly responsible for the severity of the fires in Los Angeles, is that the last 2 years have been very wet. This year's been extremely dry. Lots of vegetation build up. It's now really desiccated, and it was just ready to go. And this is something that we've seen in a lot of parts of the world. West Africa has had floods followed by severe droughts, followed by severe floods. And this seems to be one of the aspects of extreme weather, extreme weirding, as Catherine Hayhoe calls it, as a result of climate change. So yeah, I'd be very interested to hear anyone's thoughts on that as well. So yes, I will wrap up there. I think attribution science is super important. You know, you're doing something right when Donald Trump doesn't like it. It's the last 20 years of research. It's a very new field, but I think it has changed the way we talk about climate change. And it's easy to forget that 20 years ago, we didn't talk about climate change and how it's changed our weather. And now people are talking about doing operational attribution, where this can be incorporated in weather forecasts. It's all over the news, and it's easy to kind of miss where that's come from. And obviously these rapid attribution studies let us join that conversation while it's still happening. But we are aware that there is more that we could do. and that we could probably do it better. So I would love to hear your thoughts, also your questions. If you want to know more about what we do, have a look at the website, but the Imperial servers went down today, so it might not be up at the moment. So save the bookmark if you want to have a look at it. Done.
Okay, thank you very much indeed, Claire, for a whistle-stop tour through some really quite important work, I think. I can imagine some of the statisticians in the room are kind of thinking, really, they do that? And I think it's really important to remember that second bullet point. This is time critical, the work. You've got 3 weeks to do it. So we can't afford for a PhD student to spend 4 years analysing one data set. So I guess some corners have to be cut.
I mean, if you have a PhD student that you can get to work on how we can do it rapidly in the future, that's great. We just have to have the methods peer reviewed and ready to go before we can deploy them. Great.
No, that's fine. I was just going to say, so I wonder if anybody's got any questions or comments from the room. And I also have a look online in case anybody's got anything there as well.
Oh, shock and all.
Yes.
Ew.
Just on the last thing, is it possible to create models that show those sort of combined factors? Yeah, I mean, for instance, so that's in your one. Yeah, so something that shows that combined effect is going to bring about.
Do you mean a statistical model?
Yeah.
Okay, so yes. So the question was, is it possible to essentially create an index that captures that climate whiplash effect? In essence, I think that's, yeah. There is a paper by Daniel Swain that came out this year that everyone has been talking about. If you Google climate whiplash, I'm sure it's what will come up if you put it into Google Scholar. I can't remember how he did it. I did skim read it earlier and thought, yeah, that's not going to work for this study. And I can't remember exactly if it was a specific index or if he just talked about changes in the variability. I guess what you could do is look at absolute differences year on year, but you would need to know exactly what you... It comes down to this question of event definition, like what exactly would be the difference that you consider to be significant, over what period, over what seasons. It gets very difficult to... Certainly to come up with a general index, I think would be very hard. And that's why all of the indices that we use at World Weather Attribution, they're always tailored to the event, the specific event that we're trying to analyze. Because generalisms don't really work.
So basically, you basically ask the local experts, that's their opinion, helps to validate your opinion.
We basically co-design the studies with the local experts if we can. So, I mean, we're not experts in Los Angeles weather. We're definitely not experts in fire. So we had 4 US experts that were helping us with this, and one guy at the Leverhulme who works with us over at Imperial, well, jointly Imperial Reading, who help us to come up with what are the aspects of this fire event, what are the weather aspects that we should be trying to look at. And they said antecedent drought, the dry seasons got later, which is really the problem in this case, I think. And we looked at the fire weather index because that just captures the kind of peak fire risk. But yeah, coming up with I'd love to be able to do something about the climate whiplash. And I know there was a kind of a rapid study that came out from the UCLA guys, but I don't know what exactly the index was that they used. I've been a bit head down in what we were doing.
I see there's a comment in the chat. Let's see what it says. David Cahoon. David.
Hello.
You have yes.
Hello.
Hello. Yes, I saw you calculated the likelihood ratio as the ratio of 2 areas. I wondered if there's anything to be said by analogy with what one might do in significance testing for calculating the likelihood ratio as the ratio of the 2 densities.
like a Bayes factor.
Really hear that.
Oh, sorry. So David asked if rather than calculating the probability ratio as the ratio of two areas, whether we could do it as the ratio of two densities. So you mean using the whole PDF instead of just the exceedance probability? Bless you.
Well, using the exact values that were observed rather than greater than.
So yeah, there's kind of a philosophical point there, I guess. What we're normally looking at, actually, I should have said this earlier in attribution, we're looking at a class of events. So we would always communicate this as a value, as an event as extreme as the one that's been observed. So we wouldn't look at a point estimate because those impacts we assume would have occurred had higher temperatures occurred or a more extreme rainfall event occurred. So looking at just that one value, that kind of point estimate, unless there is a specific reason that that amount of whatever that quantity was is important, I think for what we do, looking at an exceedance probability of same or greater severity is more relevant.
Good. Thank you very much.
Any other question? Yes, question over there.
I want to ask, so you know, showing model comparison. So kind of there are some things that will be captured by one model which won't be by another type. And in the rapid study, you will use one particular model if I get correct?
That's an excellent question. Also something I should have mentioned. So the question was, do we only use one particular model in a rapid study or do we use multiple models? So what we would always try to do is to use as many data sources as we can possibly get our hands on. So what we would usually do, if we were doing something like temperature, where there's a lot of freely available data, we would look at regional models. So where you have a global climate model that's been run then with a smaller area model kind of nested within it. We would try to look at, probably for heat waves, we would also look at CMIP6 because the regional models that we use are CMIP5, which is an older generation. CMIP6, for something like rainfall, it's not high enough resolution to capture the kind of granularity of most events. But for heat waves, which are very spatially extensive and normally quite kind of smoothly varying in space, CMIP6 you can get away with. We would also try to use something like the high ResMIP simulations, which there are sea surface temperature forced high ResMIP simulations. So that's again another framing. It's not just forced by CO2 and then we let the model physics run. It's forced by observed sea surface temperatures, at least up to a point. And if we can get more models, even better. So yes, we would always advocate for using as wide a range of models to represent as wide a range of processes as possible. If they then all agree, brilliant. Actually, what we found in this study was that the CMIP5-driven Cordex models on the rainfall didn't agree on the signal, but when we added in high ResMIP models, they all trended in the same direction as the observations. So there are obviously, when you look at these different generations of models and different groups of models, they have different processes represented, they have different resolutions, and therefore they have different biases. So it's really important to look at as much as you can. As I say, with this study and with the fire weather index, it was such a small area, we needed high res data and we needed a lot of variables, and that was all that we had available.
So when you're trying to model the heat index space, if one particular model does the sea surface temperature better, but another one does the heat index better, do you go with the one that does the heat index better, or do you use the sea surface temperature one up till the sea surface temperature and then take the output from that as the input into the heat index one?
No, we would just run the same statistical approach over as many models as we have. If we find that they fail that model evaluation step, then we would discard them. So if they don't get the spatial pattern or seasonal cycle right, then they're not likely to represent those extremes very well. So we would discard them, but we would try and use as many different framings essentially and as many different models from those framings as possible.
I think there's a sort of related comment to that is, I mean, in relation to the causality. So I'm just shouting, so okay, in relation, so the Bradford Hill thing. So one of the things is the multiple strand of evidence. I think one thing that's important now, actually, it's multiple independent strands of evidence.
Oh, yes, sorry.
And looking at the model pair that you were using there, I'm not sure that they're as independent as they might be.
No. Unfortunately, we are limited to an ensemble of opportunity and we can only work with what we've got. So this is why, as I say, the physical reasoning and the expert judgment from the people that work in this area and know the literature and know that actually this is in line with what we expect to see and with these other model findings is, yeah, it's really important to have as many different strands of evidence as possible. And I should say we were not making strong statements about the fires, about the results of this study. I'm very aware of that. Yes, we were very cagey about how we kind of framed the conclusions as overall there is evidence that climate change is most likely increasing the probability of these fires. But yeah, it's a good point.
Okay, so I make it 2.
Another one.
Did we? Is it where?
I'm going to be around. You can just ask me if you like.
Yeah, we should probably leave it there so that next people can get in.
There's someone hovering.
Let's thank Claire once again for a very interesting. So Claire will be